Let's make carbon-carbon bonds. Start with a ketone. Treat it with a strong base, and that base will take one of the protons next to the carbonyl. The product of that acid-base reaction is an enolate, which I can draw either of these two ways, right? There are two resonance structures, which is why enolates are relatively stable for a carbon bearing a negative charge, right? Carbon is electropositive. Carbon doesn't like to have a negative charge on it. I could never treat this with the base and take one of these hydrogens down here. Only next to the carbonyl does it make sense, because this enolate is resonance stabilized. Like an enol, enolates are ambident nucleophiles. They can react at oxygen or at carbon, but most of the time they are going to react at carbon. And when they do, that gives us a way to use this as an SN2 nucleophile. It can react with electrophiles like bromomethane in exactly an SN2 reaction and give me an alkylated species over here. Again, draw the arrow from the enolate going to the methyl, and you kick out the leaving group, and now I have a new carbon-carbon bond, which is exciting. This is, as I said, an SN2 reaction, and so everything that we learned last term about the SN2 reaction still applies here. So what do we remember about the SN2 reaction? Well, the one thing, we want these polar aprotic solvents. So nothing too polar like water. It's usually not great for SN2, although sometimes it can work. And we usually don't want it all the way nonpolar like hexanes. Something like ether, THF, DMO, or DMSO, these are good nonpolar or polar aprotic solvents for SN2 reactions. Remember that we can't have this bromomethane, this electrophile, be too crowded. If this is too crowded, too sterically hindered, then the nucleophile can't do the backside attack that it needs to do for the reaction. So tert-butyl bromide or something like that, SN2 is not going to work. In that case, what would actually happen is an E2, an elimination reaction. And a lot of times E2 and SN2 might be competing with each other, and that's particularly true at a higher temperature. So very often when we're doing this reaction, we're using very strong base to deprotonate the ketone, but we're also doing it at very low temperatures. 0C, maybe even in dry ice and acetone, so negative 78 Celsius. It's very common. So it's an SN2 reaction. It's probably the most important and most useful SN2 reaction to the synthetic chemist. So what base should we use? First of all, we need a really strong base so that we can fully deprotonate our ketone. So we need all of our ketone to go to enolate for this reaction to work. Later on, we'll talk about what kind of reaction will happen if we don't have that. But for now, believe me that we need a strong base. So let's talk a little bit about base strength. So to know base strength, we need to know the pKa's of the conjugate acids. So here is our pKa number line. I think you might have seen this before. So for instance, water is pKa around 15. These are all rough estimates. Most ketones are around 20. Alkynes are around 25. Amines are 33, 35 in that area. And then alkanes are way, way, way down, almost off the scale, higher than 40, as high as 48 or so. So what does this mean? So if we look at the conjugate bases of those things in black, now we can kind of get a sense of base strength. So the strongest base that we've got here is butyllithium, right? That should deprotonate just about anything else on this chart. These amides, which is what we call the conjugate base of amines, those are pretty basic too. Alkynes even are pretty basic. And here is our enolate that we're trying to get. So the point here is that OH minus is not going to cut it, right? So OH minus is a good 5 pKa units less basic, which amounts to 5 orders of magnitude in equilibrium. So if we just use NaOH to try and deprotonate our ketone, it's probably not going to work very well because only one 100,000th of the pot is going to be enolate, and most of it's going to be pure. So anything in that direction should be good. So why don't we just reach for the best one, butyllithium? The reason that we don't use butyllithium is that it's nucleophilic. We've actually already studied this. So alkyl lithiums are just like alkyl magnesium bromide, which is to say the Grignard reaction. So if I treat a ketone with butyllithium, it's much more likely to just add in to the ketone like a Grignard would, and then my product looks something like that. Okay, so butyllithium isn't going to work. It's the strongest base we've got, just about. So base strength isn't the issue. The issue is that it's too nucleophilic, so we've got competing reactions. So what I need is a strong base that is non-nucleophilic. The most common strong non-nucleophilic base we'll use is called LDA, lithium diisopropyl amide. So you start with diisopropylamine, you purify it, you deprotonate it with butyllithium, which again is a really, really strong base, and that is how you get LDA. So LDA, we've talked about it a little bit in 250, but this is a great example of a bulky base. These things are antlers, right? So we said, that makes it hard for it to sort of get into stuff. And so these antlers are going to make it much less nucleophilic, even with reactive electrophiles like ketones. Now, even given that, we're not going to take chances. We're going to run this as cold as we can to make sure that the reaction is selective, right? So the colder it is, usually the more selective between two reactions it is. But these are really, really common conditions. So we'll either make LDA ourselves or buy it, and then we'll treat our ketone with LDA in ether at very, very low temperatures. -78 happens to be where a dry ice acetone bath lies, so that's usually the number that comes out. It's a very fast reaction, takes minutes, and then you add your alkyl with a leaving group, bromide, iodide, chloride, and you, again, can make that bond. But when you're alkylating a ketone, it's important to have a strong non-nucleophilic base. NaOH, not strong enough. Butyllithium, strong enough, but too nucleophilic. LDA, very strong, non-nucleophilic, especially at cold temperatures. This is a good way to get an enolate, which you can then alkylate.